The next decision in the CAPI snap process is to pick the snap job mode. There are two choices: job queue mode and direct access mode. In job queue mode, shown on this diagram, the application explicitly calls for an acceleration algorithm that completes and returns results after each call. These calls work like a function call in C or other programming languages. A call can have parameters and return values. The calling application thread waits until the call returns. The application can make multiple calls, and Snap will maintain a job queue on behalf of the application, hence the name. You can also have multiple applications calling for the accelerated action simultaneously. Again, the Snap infrastructure maintains a job queue for all of the jobs, keeping the context separate, scheduling the work between multiple actions, if available, and returning results individually for each call. The action itself may require data from any source, not just memory. For example, a job queue mode request might be for the action to fetch two separate arrays from storage, perform an intersection on the data in the arrays, and store the results in server host memory. Parameters in the function call could define the addresses and the corresponding I/O interfaces, similar to pointers used in a C function call. Direct access mode is a different paradigm from job queue mode. In direct access mode, the application still starts the accelerator, but the accelerator will run continuously, working on a constant set of data. For example, the accelerator may be designed to scan all incoming TCP/IP packets, looking for rogue requests or denial of service attacks. In a different case, the accelerator might be monitoring incoming video, searching for specific patterns, or filtering for regions of interest. In both of these cases, once the job starts, it continuously runs. The accelerator may send interrupts, set memory flags, or wake up threads upon detecting interesting events, but it runs constantly until the application shuts it down again. This is comparable to starting a worker thread in traditional programming. The calling thread and the worker thread execute concurrently and communicate with each other. For our Hello World exercise, we will use the job queue mode from the previous slide. The final step in the preparation phase is to specify the API by which your application will call for the accelerated action. As described in the preceding CAPI Snap overview, the API will need to specify three things. First, which accelerated action the application wants performed. Second, one or more pointers to the source data for the action. Third, one or more pointers to the destination location to store results. Once called with these parameters, the CAPI Snap infrastructure will manage the job, assist in accessing the data, and return the results as applicable in the chosen CAPI Snap mode. There is a set of questions to answer when deciding on the API. First, when calling the action, are there parameters needed to perform the action? Depending on your action, it may have no parameters, one or more. For example, if you were doing a character search operation on an incoming dataset, you might send the search string as a parameter, or a table merge would need to know which columns or rows to target. Next, you'll need to point to the source of your data. Is it coming from host memory, or maybe from the 2 TB of NVMe on the Nullitech 250S card? In any case, you'll tell Snap where the data is located, the specific start address, and the size of the data. In some actions, you may need to specify more than one set of source data. This might be the case in a database intersection action, where 2 or more datasets are read and the resulting action gets performed on all of the datasets. CAPI Snap allows you to use multiple source pointers concurrently. Depending on the snap mode that you chose earlier, there are specific questions needed to define the API. For job queue mode, where there are individual jobs, each with explicit start and end, each accelerated function call will simply return when the work has completed. If there are results, the action will return them in the predefined return value area, or it will store them to a specified destination location. Just like with source data, you can specify any of the different location types, address and size. If you are in direct access mode, you may need to do some initialization work, like open up channels for incoming streams. You will also want some kind of interrupt, memory mapped I/O register, or host memory flag to inform the application of an interesting event. You can define memory mapped I/O registers so the application can monitor action progress or even change modes of action operation. This is useful for long-running actions, where intermediate progress and results are of interest. All Snap API calls use a similar structure, starting with the queuing of the work item, containing return codes and flags. The rest of the structure is action-dependent. Here we show 3 different action examples we've created and the associated structures. The hash join example requires 3 table addresses, T1 and T2 for input, T3 for output. The results are the number of table elements processed for each of the tables. SHA-3 requires only few parameters to configure the checksum type and the initial checksum. The main output is the new checksum. The intersection example, again, has 3 pointers, one pointing to data in host memory, the second to data in on-card memory. The result could be stored in host or card memory. All of these examples are in our CAPI Snap GitHub repository and can be used as a basis for your development.